Assalamualaikum and hi everyone. Alright, so today we're going to talk about Dalton's law of partial pressure. Okay, on my previous video, I already explained to you what is Dalton's law of partial pressure. So our focus for today is on how to use different formula to calculate the partial pressure of gases. Okay, so let's recap with a few important things. Alright. So this is definitions of Dalton's law, where it states that total pressure of a gas, so total pressure of a gas in a container is the sum of partial pressure exerted by individual gas present in the container. Okay, so let's look at the diagram given in the screen. Okay, so we have here gas A, red molecule, gas B, yellow molecules, and gas C represented as a blue molecule. Alright, so this gas A, B, and C will be mixed together in a container to become a mixture of gas. Okay, so basic example or simplest way to understand partial pressure in Dalton's law. Okay, so total pressure is equivalent to partial pressure of gas A, partial pressure of gas B, and partial pressure of gas C. So P total in this container equivalent to PA plus PB plus PC. Okay, let's look for a different example. Okay, so this is the first example. Okay, in this vessel, okay, I have a mixture of hydrogen gas, so H2, okay, and then oxygen gas, okay, Cl2, and another one is CH4. So 4 different gases mixed up in the same container, or mostly we name it as a vessel. So P total of this vessel is equivalent to partial pressure of hydrogen plus partial pressure of oxygen plus partial pressure of Cl2 plus partial pressure of methane, CH4. Okay, so there are 3 ways on how you can calculate partial pressure of individual gas in a vessel. Okay, so first, using the basic one, Boyle's law, which is P1V1 equals to P2V2. Okay, for you to use this Boyle's law, in the question, it must state that it is a constant temperature as well as amount of gas. Okay, second one is we are using ideal gas equation. Okay, so ideal gas equation is made up of P, V, and RT. Okay, so gas here represent what kind of gas? Okay, let's say we want to find out the partial pressure of nitrogen. So P N2 V equals to number of mole of nitrogen gas RT. Okay, so if you are using this ideal gas equation, you have to remember you need to use the right unit for each variables used in this equation, where is pressure is used in atm, volume in liter, number of mole is in mole, gas constant. So we have 2 different value of gas constant in our list of constant. But for this one, we're going to use 0.08206 per mole per Kelvin, liter, and atm. Okay, and temperature we're going to use in Kelvin. Okay, so third one, we're going to use a mole fraction, where P gas means the total pressure. Oh, sorry. Okay, it's not a total pressure, but this one is what kind of gas we are looking for. Okay, so let's say if pH2, then mole fraction of hydrogen gas times with the total pressure. Okay, so we're going to look at each one of these in a different example so that you can understand better what kind of question require which formula. Okay, so this one, the first one, is using Boyle's law. So 2 flasks are connected with a stopcock. Okay, so let's say imagine this is a glass or flask or vessel, whatever it is, it's just the same meaning, are connected with a stopcock. So this is a stopcock. Sometimes it's also referred as valve. Okay, the first flask has a volume of 5 liters and contains nitrogen gas at a pressure of 0.75 atm. So 5 liter is the volume, and the pressure of nitrogen gas in this one is 0.75 atm. The second flask has a volume of 8 liters, okay, and contains oxygen gas at a pressure of 1.25 atm. So when the stopcock between the flasks is open and the gases are free to mix, what will the pressure be in the resulting mixture? Okay, so that means you need to calculate partial pressure of nitrogen after mixing and partial pressure of oxygen after mixing. And the question wants you the final pressure. Okay, so we need to find out what is the final volume after the two gases are allowed to mix together. So V final for both cases is the total volume of both flasks. So first flask is 5 liter plus the second flask is 8 liter. So in total we have 13 liter. Okay, so need to calculate for nitrogen first. So P1 V1 equals to P2 V2. So pressure 1 is 0.75 atm. Okay, so V1 is 5 liter. Alright. P2 is what we're going to find out, and volume 2 is the new volume after mixing, which is 13 liter. So now try to calculate P2, which is the new partial pressure for nitrogen. Okay, so if you calculate, you will get the value of your partial pressure of nitrogen after mixing is 0.288 atm. Okay, so this is for nitrogen after mixing. Alright, so now let's calculate for oxygen. Okay, so again P1 V1 equals to P2 V2. Okay, so pressure 1 first for oxygen gas is 1.25 atm. The previous volume is 8 liters. Okay, P2 is the new pressure, and final volume is 13 liters. Okay, so try to calculate what is the new pressure for your oxygen. So if you press your calculator, you will get your answer to be 0.769 atm. Again, I want to emphasize you to always include unit. Always include unit in the calculation. Okay, the reason why is because we want to make sure we are using or we getting the same unit as the final answer. Alright, so now this is the partial pressure of nitrogen, and this is the partial pressure for O2. Okay, so now let's calculate the final pressure. 0.288 atm plus 0.769 atm. And second one, besides you have to make sure you always include unit in the calculation, you also need to remember, try to avoid as much as you can rounding off the final the answer in the closest value. I mean, like you leaving it with 1 decimal places, 2 decimal places. At least leave it up to 3 significant figures of 4, and you can only round off at the final answer. Okay, so this is the answer. 1.057 is the total pressure after mixing. Alright, okay, so as you can see in the problem statement, for this one, they only give you volume initial and then initial pressure of each gases. So, and then the gases are allowed to mix, and so you have to find out what is the new pressure. Okay, so there's no mention about temperature or the amount of gas. So definitely we cannot use PV equals to nRT. So no information for number of mole and temperature. So the only allowed formula that we can use is Boyle's law. Okay, let's look at the third example. This one we're going to use ideal gas equation. So 1.5 liter sample at 298 K, which is your temperature, contains 0.030 mole of nitrogen gas and 0.020 mole of oxygen. Okay, so oxygen, okay, nitrogen. Sorry for the typo. I forgot to write down N2, which is the number 2, as the subscript. Okay, so that's why it appears in that way. So if the total pressure of the system is 0.25, so this is PT is equivalent to 0.52 atm. Alright, so what is the partial pressure of the two gases? Okay, so we're going to use PV equals to nRT. Alright, so P, okay, let's look for oxygen first, N2. So P N2 equals to V equals to, sorry, problem, I need to clean off this first. Okay, we don't have any eraser button here, so shall we just cancel it out? Okay, so for N2, okay, so N2, P N2 V equals to N2 RT. Okay, so P N2 V equals to N2 RT. So P N2 is what we're going to find out. So V is the volume of the sample or volume of the system, which is 1.5 liter. N stands for number of mole, and I already mentioned here which is for nitrogen gas. So it's 0.030 mole. Okay, R is a constant, which is 0.08206 per mole per Kelvin meter atm. Okay, and the temperature is already stated in Kelvin, so you just need to substitute into the formula. Okay, so first mark always be writing formula. Second mark is your substitution, and finally you get the answer. So rearrange, you will get the partial pressure of nitrogen. Okay, again try to press your calculator. Okay, if you press your calculator, you will get the partial pressure of nitrogen is 0.489 atm. Okay, so you can calculate partial pressure of oxygen using the same formula, or you can just simply subtract the value from P total, because it already mentioned to you the P total is 0.52 atm. Okay, so P total is partial pressure of nitrogen plus partial pressure of oxygen. Alright, so 0.52 atm equivalent to 0.489 atm plus PO2. So your PO2 is actually alright, so 0.031 atm. Okay, so if you don't want to use this kind of method, you can also just using the same formula as you do in your nitrogen gas. By right, you should get the similar answer for your oxygen gases. Okay, so in this point, using ideal gas equation, so definitely in the question, they need to give you all the information needed, okay, which is P total, volume of the vessel or flask or container, number of mole, and temperature. Okay, alright, or they give you, instead of mole, they will give you mass of gases. Okay, so by the mass of gases, you need to find moles, okay, which is mole equivalent to mass over molar mass. Okay, so you just need to remember the volume here referring to volume of the vessel. It's not volume of the gas, it's volume of the container, vessel. Okay, so temperature is temperature of the system. Okay, so let's look at the Next example, so using mole fraction. So again, try to remember, if you are trying to use mole fraction, it means you need to have mole of gas and mole of mixture. Okay, so a mixture of gases containing 2.14 gram of nitrogen, 5.85 gram of hydrogen and 4.18 gram of ammonia. If the total pressure of the mixture is 4.58 atm, what is the partial pressure of each component? Okay, so they just give you mass and final pressure, total pressure. So you cannot use ideal gas equation because they don't give you the temperature and volume. Okay, you also cannot use Boyle's law because there is no information about volume either. Okay, so this one is straight away you're going to use mole fraction. Okay, so first you need to find out the number of mole for each gases. Okay, so N and 2. Okay, shows all your calculation. So 2.14 gram divided by molar mass of nitrogen, which is 14 times 2 gram per mole. Okay. For hydrogen, okay, press your calculator for that one. For hydrogen, 5.85 gram divided by 2 atoms of hydrogen, and each one is just 1. So it just gives you the same value as the mass, but you need mole. And for ammonia, okay, so 4.18 gram divided by nitrogen is 14 gram per mole plus 1 for hydrogen. Okay, so try to press your calculator for all. Alright, so for nitrogen, you will get the number of mole to be 0.0764 mole. Okay, and for your ammonia, you will get the number of mole to be 0.246 mole. Okay, so for you to use the mole fraction, okay, let's say first we're going to find out partial pressure of nitrogen. Okay, is equivalent to Xn2 times with the P total. So Xn2 is 0.0764 mole divided by N total. Okay, so N total is, you just need to sum up the mole of nitrogen, which is 0.0764, plus with the number of mole of hydrogen, okay, and plus with number of mole of ammonia. Okay, so equivalent to Nt, let's write down here, 6.1724 mole. Okay, so we can replace here 6.1724 mole. Okay, time with the total pressure of the gas, which is 4.58 atm. Okay, press your calculator. Okay, so if you press your calculator, you will get the partial pressure for nitrogen is simply 0.0567 atm. So the unit of partial pressure must follow the unit of the total pressure. Okay. Secondly, try to calculate PO2. Okay, sorry, we don't have oxygen here. pH2. Okay, so 5.85 mole of hydrogen over total mole done with the total pressure 4.58 atm. Okay, press your calculator again. Okay, so you will get the partial pressure of hydrogen to be 4.340 atm. Okay, you can do the same step for ammonia. Okay, so you can using P and H3 equivalent to X and H3 times PT to get what is the partial pressure of ammonia, or simply P total, okay, use the concept of Dalton's law, equals to Pn2 plus PH2 plus PnH3. So we already have total pressure, which is 4.58 atm. Nitrogen gas to be 0.0567 atm. Hydrogen is 4.340 atm. Okay, so now we just need to find out what is the partial pressure of ammonia. By how? Just simply subtracting the total pressure with the pressure of the other two gases. If you do so, you will get the value of partial pressure of ammonia, okay, to be 0.1833 atm. Okay, so this one using mole fraction. Okay, as you can see in the question, they don't give you any information about volume or temperature, so you only have on how to calculate moles and given the total pressure. So just use the concept of mole fraction and with the total pressure. Okay, the applications of Dalton's law in experiment or in chemistry is in the water displacement method, where water displacement method is an experiment to collect gases over water. Okay, so in this flask, we have a reaction which produce gas, and these gases is allowed to pass through this U tube. Okay, this tube, glass tube, okay, and then it's collected over water. So this test tube will collect the gases. So the volume of the gas collected here, okay, the volume of the gas collected in the test tube is going to be used to calculate the pressure of the gases. Okay, so we're going to use the Dalton's law concept here, where total pressure is equivalent to the partial pressure of the water and partial pressure of the gas. Okay, normally we only collect one kind of gases in water displacement method. Okay, so partial pressure of water is the vapor pressure of the water molecule. Okay, vapor pressure of water molecule is interchanged depending on the temperature of the water. Okay, so normally the vapor pressure of water molecule will be given in the question, okay, according to the temperature of the reaction mixture. Okay, normally we will carry out our experiment at the standard room temperature, which is 25 degrees Celsius. Okay, and total pressure is normally equivalent to atmospheric pressure, which is 1 atm or 760 millimeter mercury or 760 torr, or any other unit of pressure that you know, which is Pascal and Newton per meter square. Okay. P total, okay, so this is all the definition. You can just simply read it. So now let's try to apply the concept of Dalton's law in the concept of water displacement method. Okay, look at the question given here. So by using water displacement method, 128 ml of oxygen gas was collected from the decomposition of potassium chlorate at 24 degrees Celsius and atmospheric pressure of 762 millimeter mercury. Calculate the mass of the oxygen gas obtained, which is your oxygen, okay? The vapor pressure of water at 24 degrees Celsius was given as 24 millimeter mercury. So the question wants you to calculate mass of oxygen. In order for you to do so, you need to first determine what is the partial pressure of the oxygen and then calculate the number of mole. Okay, so we're going to use the concept of Dalton's law here. So P total equals to P water plus P oxygen. So given that P total is 762 millimeter mercury, P water is 24 millimeter mercury, So PO2. Alright. So PO2 simply P total minus with 24 millimeter mercury. So you will get 738 millimeter mercury. Okay, so you have volume. So this is the volume. You have temperature. Okay, temperature is 24 degrees Celsius. If you convert to Kelvin, just plus 273.15, okay, equivalent to 297.15 Kelvin. Okay, so this is the volume. You need to convert it into liters. And you also have the partial pressure of oxygen. Convert it into ATM by 738 millimeter mercury divided by 760. So you will get it 0.971 ATM. Okay, so now you can use PV equals to nRT to get mole of oxygen. Okay, so for oxygen, so partial pressure of oxygen is 0.971 ATM. The volume in liters, 128 over 1000 liter, equals to number of mole of oxygen. R is 0.08206 per mole per Kelvin liter ATM. Okay, time with the temperature in Kelvin, which is 297.15 Kelvin. So press your calculator to get number of mole of oxygen. Okay, so you will get the answer to be 5.097 times 10 to the power of negative 3 mole. Okay, so the question asks you for mass. So mass oxygen is simply number of mole. Okay, time with the molar mass, which is 16 times 2 gram per mole. So you will get your answer to be 0.163 gram. Okay, so simple as that. The concept of Dalton's law is applied at the top, okay, to calculate the partial pressure of the gas, oxygen gas, which is collected over water. Alright, and then from the calculated partial pressure of oxygen, you get to find what is the mass. So two different formulas of pressure is being used here, which is Dalton's law as well as ideal gas equation. Okay, so before we end our lesson today, okay, I just want to give you a final exercise. Okay, exercise. So this one, you need to come up with a solution. I'll give you a day, not a day. Okay, after you watch this video, please submit to me in our Telegram group on your calculation for partial pressure of each gas. Shows your calculation and then we are done. Okay, so see you guys in my next video. Thank you. Stay safe.